All right, another week, another video, another snow day. So the next unit, which you'll do the first assignment from, is going to be mostly review, though a couple of new things, and it's about sequences and series. And really, the bulk of the unit, the next unit, is going to be about series. And you'll recall that the difference of sequences is like A1, A2, A3, A4. It's a number sequence, the Fibonacci sequence, the sequence of odd numbers 1, 3, 5, 7, 9. Those are sequences. A series is when you start adding together the numbers in a sequence. So A1 plus A2 plus A3, etc. All right, so that's the major difference between, and that is the difference between a sequence and a series. So we're going to spend most of the time looking at series. Most of the entire next unit is series and the power of series, and they're extremely powerful things, as you'll see. I think the homework in the sequence section, which is the first section of chapter 11, should be pretty straightforward. It should be pretty much review. One word that comes up is whether a sequence diverges or converges. If it converges, it goes to a number. If it diverges, it doesn't. Another word that will come up that's new is this word monotonic. And here they have a definition. If a sequence is called increasing, basically if each term is bigger than the previous one, and it's decreasing if each term is smaller than the previous one. And any series that's either increasing or decreasing is called monotonic. And that's one it's a term that'll come up a bit, and it's one that you guys just should be familiar with because you'll see it here and there. All right, right here is a series that you guys should all know. It's the geometric series, and this is an infinite geometric series. That will converge if the absolute value of r is less than 1, r being the multiplier each time in the series. The sum of it is the first term, whatever the first term of the series is, divided by 1 minus r. You guys proved this last year in pre-calculus, and I'll put a link to the video, or a link to a video of the proof in my email, but it's one that if you don't remember the proof, it's worth re-looking through. It's a beautiful thing. But this series is really important, and we'll have a couple different uses for it. Yeah, so make sure that you know this. This is really an important one. All right, so this right here, this is example 6 out of section 11.2. Find the sum of the series n equals 0 to infinity of x to the n, where the absolute value of x is less than 1. And if you write out their first few terms of this series, you'll see that it's 1 plus x squared. Oh, it's a geometric series, and the first term is 1, the multiplier is x, and so this series will sum to 1 over 1 minus x. Now, what I'm going to do is there'll be a link to a Desmos thing that demonstrates this really well. And it's kind of cool to see. You'll see that, again, this series will turn into this function here. However, it only does it for the interval from -1 to 1, because that is the interval of convergence from -1 to 1. And it's pretty neat. So look for the link will be in the email. So here's an interesting series, and the question is, it asks you to show that this is convergent and then find its sum. And if you start looking at it and you write out the first few terms, when n equals 1, you have 1 over 1 times 2, and then you add when n equals 2, 1 over 2 times 3, plus 1 over 3 times 4, plus 1 over 4 times 5, plus 1 over 5 times 6. 5 times 6, plus ... And when you look at this, it's 1/2 plus a 1/6, plus a 1/12, plus a 20th, plus a 30th. The next one would be plus a 42nd. And it doesn't look like it. It's pretty hard to see what this adds to. And this is what makes this one pretty interesting. If you're looking at it this way, you won't be able to tell what it adds to. However, if you go back to the original problem and you break this up by partial fractions, you'll find that 1 over the quantity n times n plus 1 is equal to 1 over n minus 1 over n plus 1. So if you start looking at this series, the series will add to, well, if you plug in 1, you get 1 over 1 minus 1 over 2. That's plugging in n equals 1. And then when you plug in n equals 2, you get 1/2 minus 1/3. You plug in n equals 3, and you get 1/3 minus 1/4, plus you plug in a fourth, you get 1/4 minus 1/5. You can kind of see what happens here. This is called a telescoping series. We just expanded this, and you'll see that there'll be a ton of canceling. Boom, 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 boom. Everything cancels here. And if I've added up the first k terms, they'll add up to 1 minus 1 over k. So as k goes to infinity, as the number of terms goes to infinity, you'll see that this part here will go to 0, and this entire sum will equal 1 as k goes to infinity. So the limit there. So that is the sum of the series. It is 1. So here's an example of a telescoping series. All right, here is a very well-known and famous series. It's called the harmonic series. It's so well-known that it actually gets its own name. It's the harmonic series. And it is the sum from n equals 1 to infinity of 1 over n. So 1 plus 1/2 plus 1/3 plus 1/4 plus ... And show that this is divergent. And there's a couple different arguments for it, and we'll see some in the coming weeks. But here's one that is kind of interesting and kind of neat that someone thought this through. And figure this part out. Make this a little smaller, make this a little bigger. So this is what they figured out. So yeah, I just copied this from the book to save myself a lot of writing. But they said, okay, when you start figuring out the sum, and the first two terms will be 1 plus 1/2. And if you add up the first 4 terms, it's going to be 1 plus 1/2 plus 1/3 plus 1/4. But since 1/4 is smaller than 1/3, that this partial sum right here has to be less than 1 plus 1/2 plus 1/4 plus 1/4. And 1/4 plus 1/4 is just another half. And 1/2 plus 1/2 is 1. So that right now the sum is, this sum right here has to be greater than 1 plus 1 plus 1, which is 2. And then they say, okay, well, let's say we add a few more terms. So let's add a 5th, a 6th, a 7th, and an 8th. And if you look at these terms, well, each one of these little pieces here is going to be bigger than an 8th. And there's an 8th there, an 8th there, an 8th there, an 8th there. So these part right here all are going to be, has to be bigger than the sum of 1/8 plus an 8th plus an 8th. And again, 1/3 is bigger than 1/4. Well, these two add to 1/2, and these two to 1/2, so it tells me that this sum right here has to be bigger than 1/2 plus 1/2 plus 1 plus 1/2 plus 1/2 plus 1/2, which is 1 plus 3/2. Okay, now it's like, all right, let's look at a bigger sum here. Let's add up the first 16 terms. Well, each of these guys is either bigger or equal to 1/4. So I can say that, and then each of these guys is bigger than or equal to an 8th, and each term in this little chunk here has to be bigger than or equal to a 16th. So that means that this sum right here has to be bigger than this sum. And this little part here adds to 1/2. This part here, you'll have 8 1/8, or excuse me, 4 1/8, so that adds to 1/2. You have 8 1/16, which is 1/2, so that this sum here must be bigger than 3. And you can see that you can keep going with this argument. You have to grab more and more terms each time, but what's going to happen is the sum of the first 2 to the nth terms is always going to be bigger than 1 plus n over 2. One thing I've got here, you can't see it, but I've got a spreadsheet where I started adding up a bunch of terms. And if I add up the first 100 terms, it adds to about 5.19. If you add up the first 10,000 terms, let's see, whoops, I went past that. I'm about 100,000 terms right here. And at about 100,000 terms, it's around 12. And then I decided to add up the first million terms of this, and the sum is just past 14. So it's kind of crazy. This thing grows very slowly, but I can tell you that if you added infinitely many terms, this thing will grow to infinity. It just takes a a lot of terms to get that high. So again, by the first million terms, it's only got up to 14.4-ish. So it's divergent, but it's a very slowly divergent series. So in this chapter, we're going to learn a bunch of different tests for convergence or divergence. And the first one's got a very simple name. It's just called the test for divergence. And it says that if the terms of a series do not go to zero, then the series is going to be divergent. In order for something to diverge, the terms have to get small. They have to go to zero. If not, all bets are off. It's done. It's going to be divergent. If it goes to zero, we just saw on the harmonic series, 1 over n definitely goes to zero, but that series divergence. So if it goes to zero, we're not sure, but if it doesn't go to zero, definitely divergent. So this example here illustrates that pretty well. And if you look at this, yeah, you don't know if this series diverges. Well, it says show that it diverges. Well, what you can do is you can look at it and see that as n gets pretty big, as n gets bigger and bigger, the terms of this will get closer and closer to a fifth. And if you think about it, eventually we're adding something that's really close to a fifth, plus a fifth, plus a fifth, plus a fifth. And you can see pretty easily that that's just going to go off to infinity. So this one definitely diverges. And we don't have to do any other tests that we're going to learn later in this chapter. So it's the first thing you want to check for. Make sure the terms go to zero. If not, done. Diverges. All right. So hopefully this will help you for the assignment that I'm giving you. Thanks a lot.